Hello, my name is Stan. I worked on the data center power converter project in fall 2019 and spring 2020 with Tristan and Jason, with Professor Badawi as our advisor. I've been asked to kind of give a brief overview of what we worked on, where you guys can find all those files, and also some information about LLC converters in general. So here's what an LLC converter looks like. It has the name LLC because there's, as an example, there's a capacitor, an inductor, and there's another inductor here, which is the magnetizing inductance of the transformer. But anyway, so we have a half bridge here, resonant tank and transformer, and then rectification, and then, your output stuff there. You'll see two versions of these. If you're using a transformer with one primary and one secondary, you'll have a full bridge rectifier here. If you're using a center tapped secondary, then you'll use two diodes, and that's typically what you do if you're using synchronous rectifiers. So here we have a gain frequency plot for an LLC converter, and on the x-axis we have the normalized switching frequency with the resonant frequency here in the middle, and on the y-axis we have the gain. And this is only the gain of the resonant tank, not the transformer, which is something that wasn't very clear to me at first. So the transformer will be doing all of the stepping up or stepping down. And if you have a full bridge here, then this is going to be a 4-to-1 transformer. In our case, from 48 to 12, dividing by 4. If this is a half bridge, then this will be a 2-to-1. You control the gain of the converter by moving around the switching frequency above or below the resonant frequency. So if you want to decrease the voltage, then you'll increase the switching frequency. And if you want to increase the voltage, you will decrease the switching frequency, sort of moving up this curve here. The line connecting these peaks defines the capacitive region, and you want to stay out of that. So you'll always be working on this side here. The problem is that in the capacitive region, the current leads the voltage, so the current in the MOSFET will switch direction before the MOSFET can switch off, and that leads to conduction of the body diodes. One of my assignments for this part of the project was to generate these frequency curves, so I wrote two programs for that. So here they are in the root directory, and I'll show you where all my files are. They're under 48 to 12. We have LLC references here. These are all, there's a lot of them, but they're all very good. So I definitely recommend looking through all of them. My simulation files are all in Stan LLC. Here we've got some presentations. The one you saw earlier is LLC Converter Design. I also have Hybrid Hysteretic Control, and those are pretty much the only good ones. So the first harmonic approximation, which is what we call the process of generating those curves, is in this folder here. And what I'll do is I'll switch to MATLAB and I'll show how they work. So we'll run generic, which just takes Q, or range of Q as an input, and M, which is the ratio of the combined inductance over the resonant inductance. So here's one of those curves. Now, suppose we want to run it at a Q of 0.7, but we need a little bit more headroom, so we want to make sure that we stay above 1.5. What we can do is we can reduce M a little bit. Let's just do 2.5. And you'll see that now we easily clear 1.5. The trouble when you're designing these things is that it's sort of a balance. The higher your value of M is, the more ideal your transformer is, and the more efficient your converter is. So you want to keep M as high as possible while also hitting your target here. Another script I have here is FHA min-max, and V6 just means it's the 6th version of a converter that I've built. This one here actually lets you put in your resonant capacitor, resonant inductor, and magnetizing inductance values, which, I'll go back, you get by choosing M, choosing Q, and then solving this system of equations here. And this lets you put in a minimum power and a maximum power, so this will show you how your converter will perform at different loads. So you can see here that at 1 kilowatt it's just about reaching 2, and then this was a little bit higher than needed, but I wanted to give the extra headroom for another simulation. Finally, SFHA here. This one might be a little confusing. It confuses me. This one will solve these values for you. So it'll tell you, with the values that you've put in, what your switching frequency came out to be, what your output resistance should be, and gives you your Q and M. But these graphs aren't really generated by those values. It was a way for me to use the same program to do two different things. So next we'll move over to a simulation of an LLC converter. Here under root directory 48 to 12, stan LLC Simulations. This is where I keep most of my simulations. The old ones I've put in here, but I tend to want to go back and see how things have changed, so I've just been putting them in the old folder. So this one is the Simulink file. This requires the Simscape add-on to Simulink, but they're very generous with trials. I think I'm on like my 6th or 7th trial. Anyway, this is so here's our converter, and I'll get rid of this. Right now we're just doing an open loop, so we've just got a switching frequency of 100 kilohertz. And it should be pretty close to 11.3. What we'll do is actually reconnect this PI controller here. Come on. And I sort of just leave these blocks around so I can connect and disconnect things when I play with it. Let's see this. Okay. So what we'll do is we can use this block here, which is an ideal switch block, and we can have it close at a certain time with a certain internal resistance. So this step here closes the switch, and effectively it just doubles the load. And it's set to, I think, 10 milliseconds. Yeah, so you can see here, when we run it, this is the response to the change in current, and the switching frequency we see here goes down. So it's moving back up that curve that I talked about earlier. The other way around, it would move down that curve to compensate. This is direct frequency control, where we're just taking the output voltage and we're using that to determine the switching frequency. So it's just a PI regulator in here. Notice that the feedback is going into the positive side of this adder here, and normally you'd want negative feedback. But remember that when you increase the switching frequency, the voltage decreases. So your negative feedback's sort of already built into this here. And of course that other inductor in the LLC here is the magnetizing the magnetizing inductance that you set here. And for now, everything it is here is pretty ideal. The next step was to build this using an actual controller, which we use the TI UCC 25600, which uses direct frequency control. So let's go take a look at that now. This is the TINA simulation of the UCC 25600. I think it's about 5 years old at this point. This is the only one I can find that uses direct frequency control. The newer ones use hybrid hysteretic control, which is what Jason worked on. Actually, sorry, this is the schematic here. We had trouble getting the gain frequency plots that we wanted out of this, since this is just a transient simulation. So we couldn't really get anything too reliable. So the workaround we did for that was to add a current source here. So the switching frequency of this controller is controlled by the current coming out of this RT pin. Normally there's a voltage divider here. This sets the lower switching frequency, or the lower limit, and this resistor here sets the upper limit. You can find the values to use in the datasheet for that. So what we did to get this transient simulation working was to just add a current source here and set it into parameter stepping. leave separate cases and diagram off. Set this to be the control object, and choose what values of current you want here. So your lower limit and then your upper limit, and again you can find the values in the data sheet, the constant to multiply that by. And then when you run it, what we've done is run a transient simulation, but only have it start displaying when you know that it's reached steady state. So do some tests and make sure that you're only getting it once it's stabilized. So here's the graph, since this takes forever to run. Set the current coming out of this pin here as the first thing to plot. So you can change the order of these by doing :1 and then :2 for output voltage. I also locked up the feedback, so it thinks it's always at 7 volts. That helps it start up a little bit quicker. But what you can do is, if you've got a bunch of these simulations, and I think I did like 40 points at a time, it takes about a minute each, you can export it to a text file. And I'll show you what that looks like. What I did is I wrote a program to sort of sort through all of those. So you can see it has all of these points. So I think it's up to almost 400,000 points. And then I wrote a Python program to sort of sort through those, average them based on the current going out of that pin, which is proportional to the switching frequency. And again, if you look through this code, I'm sure it'll make more sense. And then it takes those averages, puts them into this file that we can then plot. And I'll quickly show that I think this is still good. Yeah, so these are the plots that we generated. And again, this is the fastest way I could come up of automating this. Maybe there's a better way. This shows what our predicted gain frequency responses, and then this shows what we actually measured. So here we're looking at 750 watts. And you can find the files to perform these simulations here under LLC Simulations. This might be jumping around. I'm filming this sort of out of order. But test V6 is the one with the current source. This is the program that I use to process those really long text files. And again, we believe their only chip that uses direct frequency control. But the next thing that I'd like to talk about that was another thing that I spent some time looking into is hybrid hysteretic control. With direct frequency control, the switching frequency is based only on the voltage output here. And that through the compensator, drives a voltage-controlled oscillator with a fixed dead time to drive the gates. Hybrid hysteretic control, on the other hand, and they have this in the UCC 256, 300, and 400 series chips that Jason worked on. This control scheme involves not only this outer loop, but it adds another feedback loop on the primary side here. So it's similar to current mode control, but instead of measuring the average current through the inductor, you're measuring the charge on the capacitor through this capacitor divider. And the way it does that is there are two current sources inside the chip, and they're controlled by the signals to the gates. And when the high side gate is on, a constant current is pushed into this VCR node. When the low side gate is on, that same current is pulled out of the VCR node by this current source. And that results in a combination of both the voltage across that capacitor, which is sinusoidal, and that ramp that's created by these two current sources. And that's why it's called hybrid hysteretic control, because if the ramp dominates, then it's more like direct frequency control. If this dominates, then it's more like charge control. Now this second feedback loop on the inside here, you're able to you get more information about what's going on the primary side. So you can actually have features like ZCS avoidance, where the chip knows whether you're getting into that zero current switching region and make sure to stay on the right side of that peak that I talked about earlier. You can also control the gates independently, so they have adaptive dead time, and they give the gates just as much dead time as they need to discharge the capacitance across them. The main benefit, though, to this is that it reduces the transfer function from a second order system to a first order system. So here's frequency control in blue and hybrid hysteretic control in red here. This makes it easier to design the compensator and also means you have more bandwidth, which results in a better transient response. So here's an example from TI from a power supply and design seminar. And this is the same converter under direct frequency control, and they're calling it variable frequency control here, and hybrid hysteretic control. When they stepped it from no load to full load, you can see there's a 20% deviation in output voltage. But with the hybrid hysteretic control scheme, there's only a 1.25% deviation. So that's quite a big difference, not only in the transient response, but it also means you don't have to use the same size bulk capacitors on the output to maintain the same tolerance. So you can make the converter smaller by using smaller capacitors. And if the controller recognizes that you have zero current switching by the direction of the resonant current, what it will do is it can actually skip a switching cycle, so it can actually just not turn off one of the MOSFETs just to let everything come back to equilibrium, and that's how it keeps it on the right side of that curve. Again, adaptive dead time control and burst mode, which is usually for really light loads, so I don't think that's applicable here. And I think that's all I've got for this video. Also, definitely check out Tristan's video on phase shift control because it's comparing the performance of this converter here to his it's way different. It's so much better. So both hybrid hysteretic control and phase shift control look a lot better in that respect. Again, check out Jason's video where he demonstrates the converter with hybrid hysteretic control. And I think that's all I've got. If you have any questions, either reach out through Professor Badawi or email me. I can show it here. Here, Stanley Veloche at sjsu.edu. And best of luck on continuing the project. Thank you for watching.